Hello, welcome back to another lecture on the analytical methods, statistics if you will, in ecology. This is about Z and T tests, which are fundamental beginning style analyses centered around the null hypothesis. And if you'll remember, this is classics, kind of traditional statistics, but it's not necessarily a high level of inference relative to other methods we'll try to be nudging you toward the rest of the semester. And yes, some of these statistical protocols can test your patience, but you'll see they're fairly straightforward. And as I hope you've seen already with R, you can achieve some level of competence pretty quickly just by following the bouncing ball through some of our methods that we're using in the labs. So what we're getting around to is Z and T tests. Well, I need to provide a little bit of context first that I think will maybe set up at least a way to see how Z and T tests fit within other statistics. Then we'll get around to talking about doing those tests themselves, the underlying principles in them, as well as a necessary mention of degrees of freedom, which is fundamental to a lot of the rest of the statistics for this semester. And then that also sets up, and just thinking a little bit about normal distributions writ large, that means the central limit theorem, which is another useful principle that underlies a lot of our statistics. Then there's different kinds of tests to do on the same data set. And I'm going to implement those tests, as you'll see here, Z test and a T test, both for the difference between two means, and then a T test of two independent means versus a T test of paired means. And I'm going to do that all in the same data set, and you can see, I hope, why some of those tests are not fully appropriate, depending on how you approach the data set and what question you're asking. Okay, so let's get back to context first. There's a useful flowchart that I think is useful for these classic statistics. It comes from a textbook I used to teach out of, Samuels and Whitmer. I've always found this to be a valuable framework in which to think about the choice among different statistical tests. So if we're looking at categorical responses or if we're looking at quantitative responses, constitutes here the first decision that we have to make. So if we're talking about quantitative responses to quantitative predictors, so our x-axis is quantitative and our y-axis is quantitative, then we're talking about regressions and correlations, okay? But if we're talking about categorical predictors of those quantitative responses, then we're opening up a Pandora's box of multiple sets of comparisons, some of which might include ANOVAs, which we'll get to in the next lecture. But a lot of these will then constitute, if you follow out to the end here, t-tests, t-tests, and t-tests. Or another test that might be applicable in some of those cases if your assumptions don't work. Okay? So our quantitative responses with categorical predictors can often be handled in simpler cases by t-tests, or if we end up with multiple groups, more than two groups, then we work towards an ANOVA or a non-parametric alternative. Okay, so what I'm doing is drawing the line here. Above here, we're playing with quantitative responses and categorical predictors, a number of those tests of which we can handle here today. Okay, so notice that in those cases, we're playing with normal responses, where we're assuming that we have normal distributions in our data, in our response data. Okay, and in the extra test here of an ANOVA, an explicit assumption of common variance. Homogeneous, there I can speak, variance, which we've played with already in the labs. So, also just notice that t-test, t-test, and t-test pop up here, as does ANOVA, but there's a couple different kinds of t-tests that we're going to work around with here. So, this is where we're going, and we're going to work with these Z and then ultimately t-tests as are prescribed here. But let's make the distinction first between Z and t-tests. There is a difference. They're related, but I hope you'll see how they're different too. So for a z-test, we're assuming a normal distribution, the same as for a t-test. But with the z distribution, the data are already centered on 0, which means that whatever the data might have been before, we have rescaled it so the mean is going to be 0, and therefore there is a certain number of points below 0 going negative, and a certain number of points going above 0 going positive. So this standardized distribution, which we've already seen, represents the different levels of variation you have around the mean, and that mean is now centered to be 0, okay? So it's a sample with its own mean, and it has a standard deviation, and so a z-test can then be comparing your sample to this hypothetical one here, just to simply answer the question, do you also find that a sample mean has 0? So the whole point is to evaluate a sample compared to this hypothetical one, all right? So for a t-test, it is essentially the same thing, except you'll notice that there's a number of different shapes of the curves. So they're normal-ish, where the adjustment is for how many degrees of freedom, which is essentially saying how large a sample do we have. So let's start with the yellow line. Notice that the t-test distribution for the yellow line is a little flatter. The peak is lower down and the tails are a little wider than if you had, for example, an infinitely large sample size, the topmost bar. So we shift the expectations down a bit for the expectations in a t-test based on the sample size. There's no such adjustment for a z-test. It is just assuming that you have a perfectly known normal distribution. I say perfectly known because the t-test is acknowledging that with a smaller sample size, your estimate of the distribution is imperfect. Okay? So the t-test is adjusting for the sample size. It's acknowledging that we don't have a perfect estimate of the normal distribution. Now, there's a version of this called the student's t-distribution. It's also then centered on 0, so it's similar to the z-distribution that way. It's called the student's t-distribution because this man named Gossett was working for Guinness, and their constraints on his ability to publish while he's a quality control officer for them using his own name meant that he published as a paper on this t-distribution under just the simple pseudonym student, because he was working with another statistician, Pearson, at the time, as Pearson's student. So this student t-distribution turned out to be a pretty fundamental tool for lots of analyses, and in fact is perhaps evidence to support the interesting and somewhat humorous, but maybe partially true, video that you can find on Netflix and other places on how beer saved the world. So, beer being an important part of everybody's life in college, then you should understand that the student's t-distribution is also built around beer. Well, indirectly. So, we're using a student's t-distribution centered on a 0 when we're looking at a graph like this, okay? Now, your distribution itself might have a different mean. You can adjust that and center it on 0 with a simple trick, and then the student's t-distribution can be used to analyze that. You simply use, for example, the scale command in R. So a t-test evaluates your sample compared to that distribution. And it's this sample then has its own mean, its own standard deviation. You take a sample and it has 3 different times you collect data. Well, then you see what the average is and the standard deviation is for those samples. And again, you're simply asking the question, is your sample mean equal to 0? So this sounds a little bit like a z-test and a t-test. Use some of the same jargon, don't they? And in fact, they're very similar. The distributions are both centered on 0, if we're talking about the student's t-test. The test evaluates a sample from that distribution. The sample has its own average and a standard deviation, and answers the same question, is the sample mean equal to 0? The difference between the z-test and the t-test is essentially the z-test assumes normality, whereas the t-test really becomes normal as you approach more than 30 sample size. So if you have more than 30 in your sample, your n is greater than 30 or so, you can essentially bet that you have a normal distribution. Less than that, you might be worried about the size of your distribution. This is the fundamental reason why a common recommendation is to get at least 30 to get a good estimate of a mean. So we have fairly similar tests, the z and the t-test, right? They're actually approaching the same kind of question. One just simply adjusting for sample size. So if we're talking about sample size, we do need to get to degrees of freedom, this fundamental piece of statistics, which sets up the idea of a central limit theorem as well. So let's get around to that. The degrees of freedom is the number of values in a statistic that are free to vary. Okay, so that the degrees of freedom being an expression of how many samples you have. Now, it's not simply n, the number of values. It's adjusted downward because the number of samples you're free to choose is a little different than the total n. let's think about the number of marbles in a jar, right? Let's say it's 30 or more. Okay, looks like there's a bunch in there. And if I take one of those marbles out, I was free to choose any one of those marbles. But as I work my way down to the bottom of the jar, when I get to the last two marbles, I'm still free to choose. Close my eyes, reach in there, fumble around, pull the one marble out. The last marble, there's no longer a freedom of choice. If I was to reach in there, I know exactly which marble it's going to be. So the degrees of freedom is typically expressed as an n minus 1, because there's that last marble which does not have any choice involved in its selection. Okay, so an example, 1 degree of freedom, maybe this is another way to say this. 1 degree of freedom is expressed in this simple equation here, because if I know the sum is 10 and I know what an x is, let's say 6, then I know exactly by difference what y is going to be equal, right? So if I have 2 of these pieces of this equation already answered, there's no need to try to express what the last term, y, is. I can already solve for it. There's therefore an n minus 1 degree of freedom there, okay? If I choose one, the other is obviously determined. What about if I had 2 degrees of freedom? Well, that simply means I have 2 different terms here, z being the undescribed one before. But what if I only know x? X was my 6, for example. 6 and 10, I've got 2 of those chosen, but now what I have is 2 terms, y and z, which are left to be defined. So that would be 2 degrees of freedom if I only knew x and 10, right? So it's the remaining choices, the terms yet to be determined precisely, if that helps any. Maybe. I hope my definition is useful. All right, so let's think about what does this extend to, and that is this fundamental idea of a central limit theorem. A textbook I've also used in the past defined it this way. It's the sampling distribution of the mean and it's nearly normal. The sampling distribution is nearly normal when the observations are independent and come from a nearly normal distribution. That's true for any sample size. So if I have a normal distribution, precisely normal, and I take 3 samples, there's a pretty good chance that those 3 samples will fall somewhere near the center of that distribution, simply because the most probable choices come from that center of the distribution. And the more samples I collect, the more likely it is that I'm also estimating that average fairly well. So even as low as 3, I have a fairly decent chance of hitting samples inside the possibilities, the ideal normal distribution. There's a fairly good chance that I've hit that and described the mean somewhat accurately. More and more samples, the more accurate that can get. What if my data, the true data, the underlying distribution, is not perfectly normal? What if it's still skewed, okay? The underlying distribution is skewed, and I take a sample from that skewy distribution that might have that mean. Well, even with 3, I'm still going to obtain about the same estimate because I'm randomly sampling across the most probable possibilities. If I have a uniform distribution, which is not looking very normal anymore, but it has this mean, if I again take 3 samples, I'm likely to get something that's now with a fairly broad distribution, also something that's representing the mean, and again, the more and more samples I collect, the better it's going to get at representing the true mean. What about a really wacky distribution like this irregular one? It has a mean to it, but you couldn't say that that's very normal and that most of the points fall in the middle. If I take 3 samples from that, I'm still going to obtain, most likely, a point that's somewhere near the middle, and that still has a broad distribution around it. And again, the more samples I take, the more likely I am to describe the mean of this irregular distribution. I'm not describing the entire distribution very well. I'm just describing, with more samples, what the mean is likely to be. Okay? So the central limit theorem says that for many samples, I will obtain, especially, a better estimate. So for pretty much any distribution, I'm likely to collect a data set that represents the mean fairly well, and especially so if I collect more samples than just a few. So the central limit theorem is a very convenient tool for underlying statistics because it says that we can sample and calculate the mean, especially with a larger sample size. We keep doing that, and the means themselves form a normal distribution. Let me go back and show you. The means themselves are forming a normal distribution. the means, the samples that I've collected, and the means of those samples are representing a normal distribution. So a set of replicate means should estimate a true mean. Okay? If you don't believe me, stop right now. In fact, I say, even if you do believe me, stop right now and check out this very nice demonstration online of how this works. It's essentially a randomization where beans are falling down through a cascade, and you obtain essentially a close to normal distribution with a certain number of beans, especially helping it become more and more normal. This is a nice demonstration how random sampling and collecting means can obtain normal distributions. Okay? So, assuming now that you've checked that out, and there's other demonstrations that I think that's just a nice graphical one, which is R-based, by the way, then let's think about what that means for statistics. It means that if you take a bunch of averages, you essentially obtain itself an estimate of the true mean. Sampling can yield useful information about a data set, and that means that we can compare samples to obtain real information about underlying data, even if the data are somewhat skewed in their own, okay, the underlying true data. So we can use some of these statistics then to compare means. Of course, more samples being a good thing. So let's talk about how a z-test works. We can compare two different means, again assuming that the central limit theorem can apply. Well, there's a simple data set that is available in another textbook that uses prices from the UCLA bookstore compared to Amazon in 2010, 73 different textbooks, and so they were listed by department. So this department has this course, and a textbook that's affiliated with that course at that time would cost $27.67 at UCLA bookstore, $27.95 on Amazon, slightly better price at UCLA. But of course, in another textbook and another course, you find you might actually see a much more substantial difference between UCLA. So lots of those examples, all the way down through 73 different textbooks listed here, and you get these two different histograms. Notice that those don't look very normal. The histograms of the UCLA new price looks like a lot of them are less than $50, and essentially the same idea with Amazon. So you might say, well, they look kind of similar in general, but if we're asking this fundamental question, what about the difference between those two means? That's a z-test, okay? We can ask, what is the mean of the UCLA new prices, and what is the mean of the Amazon new prices? That's different. The z-test is asking about the difference. It's asking about the difference between the books. So we're essentially analyzing this column right here, okay? Well, we're not analyzing each of those columns to the left. I'll show you how that could work in a second. We're going to analyze the differences, because we asked, are the differences essentially around 0, okay? So the differences essentially around 0 might be the case, except this looks kind of skewy, doesn't it? Here's the difference. This is the histogram of the UCLA price minus the Amazon price. And our z-test is going to ask, is that near 0? Or is it so different from 0 that we'd say there's a significant difference away from it? So if we calculate the mean, we get, with 73 books, the mean difference is $12.76. And there's a standard deviation there of 14. So the mean difference is sitting somewhere about here. As a tail skews out over here to the right, and the peak being here just around $10, so the skew pulls it out a little bit and sitting around $12 or so, okay? So we calculate a z-score for this distribution. Now remember, we're supposed to be assuming a normality here, and we might think that that's pretty close. It's lopped off with the tail down here. But what we have is then a simple z-score difference, which is saying, look at that difference, the mean difference, which is $12.76, minus the hypothetical one of 0, okay? And we compare that to the standard error of that difference, and we get this calculation, $1.67. So $12.76 minus our hypothetical 0 divided by the standard error, we come up with the z-score of 7.59, okay? So that's a standard measure of how different our data might be according to a z-score. And so then we can calculate a z-score by looking at 2 times the tail area, and that tail area at that point is this really small number, and it's a really low probability then that is a difference of 0. So our z-test of textbooks was essentially telling us that your average difference between Amazon and UCLA bookstore is not 0. We're fairly confident in that it is significantly different from 0. Now, an important distinction here is that we assumed 2 times the tail area here because all we simply asked is the mean different from 0. We didn't say which side of the tail it is. Let me go back to this. We have this distribution that comes up here to the positive end. The data are going to be up here where the UCLA price tends to be higher than the Amazon price on average for the most part. We didn't ask that question. We asked a 2-tailed test because we simply asked, is it different from 0? So if we were looking at, if we had known a priori that UCLA, if we hypothesized UCLA might charge more than Amazon, one might have only done a 1-tailed test. But our question was asking a 2-tailed test, so we need to stick to that. Although otherwise, you need to rephrase your initial question. Okay, so hopefully that gives you an example of how a z-test works. Let's look at how a t-test would work, asking the same question. Is there a difference between the 2 means? So now this flow chart pops up. Notice that the z-test wasn't in there. But let's see. We're looking at a quantitative response to categorical predictors, and I'm looking only at one group. I'm asking only about the differences, and I want to know, assuming that it's a normal response, how is that mean compared to a 0? Okay? So the t-test assumptions are that we have independent observations. Each book price is independent of the other one. They have a normal distribution, the same as we assumed for the z-test, and that we have homogeneous variance, in fact. Although unequal variances can be assumed, you can choose to do a t-test. You change one of the operational assumptions in the middle of your command line. So our defaults to an unequal one, very conveniently, where it will obtain the same answer for data that are equal variances. But if you recognize that truly we're expecting homogeneous variance, so we can sort of set this assumption aside because there's an adjustment for unequal variance. Okay, so the t-test would simply be implemented in our code with this command. We're looking at, remember, just the differences that were calculated. So we do a t-test where we want to compare it to a mean of 0, mu being shorthand for mean, and that's just simply saying that the null hypothesis is that mu is 0. So a 1 sample t-test where we're looking at the difference relative to a 0, and we get this kind of output. Okay, the data is in the difference, and the t-test score is this 7.6, which you can look up in a table. I'll show you in just a second. And the difference, the degrees of freedom, is 72. N was 73, so 73 minus 1 leading to that degree of freedom value. And we get a p-value that says that we can be quite confident that there was a difference that was significantly different from 0. The alternative hypothesis was that the true mean is not equal to 0, and I think we have support for that alternative hypothesis. We get a 95% confidence interval. There's the lower value for the confidence interval, the upper value for the confidence interval. So the mean of 12.76 could be expressed with a confidence interval somewhere between 9.4 and 16. Okay, so we have a pretty clear estimate of what the difference is between those. And remember that we had this 2-tailed test in the z-score test, right? And it was calculated out to be a pretty small value. It's also still a pretty small value, but a little bit more precise now, very small value in the t-test because we're adjusting for the sample size. Remember, z-test, we assume this essentially infinite perfect normal distribution. We have a good sample, 73 book prices, degrees of freedom 72, but it's still adjusted for that and even more precise. Okay, so we've already done a t-test where we had the same question, the same test as a z-test. We found that it worked quite well. What if we assume we have 2 different means? All right, so I'm going to work my way down through this flowchart: quantitative responses, categorical predictors. Now I'm looking at 2 groups, whereas before we looked at the difference and we only had the 1 group of numbers. Then if I instead tried it as 2 groups, for example, the UCLA price versus the Amazon price, and I assume that they're independent prices. Careful, are they independent prices? Because it's the same books, but we're going to try this anyway in case we were to go this path. And we assume a normal response, then we do this difference between the means. Okay, we're still using a t-test. So let's try it this way. In other words, what I'm saying is that this list of prices are going to be compared to this list of prices as if they were independent. Hopefully you'd pick up from my tone that that's skeptical. We shouldn't be using that because there's the same book here. They're not independent. But let's imagine that we had gone down this path on that flowchart, okay? I'm not saying you should. I just want to show you what might happen if you did. So we get these distributions. That's an independent histogram here. I say independent because it's not the same as this one, but obviously they're representing a somewhat similar shape. And the t-test of those, quote, independent means, where we have that 73 books again, would be implemented just this way. You just say t-test, the one mean, and the second mean. Remember how we did that before? We said the difference, and then we said a mu of 0. So in this case, we're assuming that they're independent, and we get this result, Welch 2 sample t-test, and we find that, lo and behold, we would not consider ourselves too confident to say that there was a significant difference from 0 here. The p-value is of 0.16, our customary cutoff being 0.05. So our number is greater than our 0.05 cutoff. We would not be confident in claiming that there is a significant difference between these two prices. The confidence interval overlaps with 0, which is another way of saying that you couldn't be confident that your number is greater than 0. Okay? The mean is 72 of one, the mean is 59 for the other, but we can't be confident about a difference between those two numbers. Well, that might be because the two data sets were in fact not normal, reminding ourselves that we had this histogram back here. Where was that? Here it is. That these things are in fact not normal. And if we use this test, we're falsely making the assumption of normality for these two independent, quote-unquote, distributions. So maybe what we should do instead for this test is to implement the Wilcoxon-Mann-Whitney test, because those data are not normal. We might be able to play around with transformations, etc., but I'm going to just show you what would happen if we used a Wilcoxon-Mann-Whitney test instead. This is called a non-parametric alternative. Non-parametric because it's not making assumptions about the parameters of the distribution, the parameter being normality. Okay, so we can implement that pretty simply. We just say Wilcox test for those same two prices, UCLA new, Amazon new, and notice that we're saying that they're paired. That's a big difference. So the fact that they're paired says that they go together, and the Wilcoxon sign rank test says that, as we expect, because of what we've seen already, there are significant differences between those two, where the alternative is that there is not. Okay, so we've seen how a t-test may be incorrectly applied in some cases if we assume that they're independent means. More appropriate would be a t-test where we acknowledge that in fact they're paired. Okay, so that would be going down this path. We went up here before where we assume that they're independent, but in fact we acknowledge then that they're dependent, and we should be using this paired t-test instead. Okay, so let's think about how a paired t-test would work. The t-test now is asking, are the differences 0? But rather than just looking at the difference column like we did before, we're looking at each number compared to its matching one. So 2767 compared to 2795, and then 4059 compared to 3114. So we're looking at these paired t-tests by comparing the pairs one at a time, essentially across the whole list. We're acknowledging that there's a matched price here, that they go along with the same textbook for the same course. Okay, so paired, recognizing that there is a reason why these numbers are aligned next to each other. So a t-test that is going to be paired, we do the same way. We're looking at the option paired equals true in R, and we're just putting in the same two prices before, but by saying paired, we're essentially saying UCLA minus Amazon. So it's another way of going after the difference column, and we get this p-value again that's suggesting that, as we saw before, there is a significant difference between these two prices. The mean, once we've done this correctly, is in fact matching the mean we've seen before, a $12.76 difference on average with this confidence interval. Okay, so what happens with a different order of entry if we put in Amazon first and UCLA new? Notice what I had before was UCLA first. What if we said Amazon is first? So we're comparing Amazon to UCLA. What we're essentially asking is Amazon minus UCLA, and we get the same answer, but obviously we get a negative mean now and negative confidence intervals because we flip the order in which we ask them. So you just have to be cognizant of the fact that you might get a different mean depending on which order you listed them, because it's asking the difference. Okay, so it's another way to analyze difference. And so let's see, what do we have so far? A z-test said that the mean price difference is not 0. The t-test, simple t-test, said the mean price difference is not 0. And the means of these things, as if they were independent, was wrong. We got a very different kind of analysis because, in fact, they are paired, they are combined. And so we get a paired t-test, and we get the same answer because it's looking at the paired differences, which is sort of like asking already to calculate the difference and then analyze the difference. Okay? So you do a t-test of the differences, or you do a t-test of the paired prices, we can get the same answer. Notice that how you do the test is going to matter a lot. So in all those cases, we had to make these assumptions about normality, and we also had to make careful decisions about the independence or the dependence of the data. Okay? So if we're thinking about those assumptions, if we're testing the t-test assumptions, in other words, we're worrying about if the data are normal. And so you've already seen this Shapiro-Wilk test. I'm going to apply it now to the Amazon data, and I find that the data are not normal. We can be fairly confident, quite confident, in claiming that those data are not normal. And the same for the UCLA test. It looks like those data could be confidently argued to be not normal as well. You can get a hint of that by looking at the box plot. Remember, it's sort of like a distribution where there's a tail comes up and the most of the data are down low. We've already seen those data distributions, and that's consistent, in other words, with those box plots. Well, what if I was to start playing around with transforms? I hinted at that as a possibility. Well, for example, if we did the square root transform, it might be argued to get a little bit better than we've seen before. Or if we did the log 10 transform, maybe better. That's looking maybe better. So the question is, do transforms help in this case? And in fact, no, 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 and no. We're not really there yet, even with transformations. So if I look at the box plots of those, you can see that even with the square root, there's still a non-centering box plots in both of these cases. They're getting better, I would say, yes, but we'd have to worry about whether the data actually fit our assumptions of normality. So if we don't have normal assumptions, we can't get them there with easy transforms, maybe what we should be doing is thinking about it. Two groups, dependent responses, so now it's like a paired kind of test. But I couldn't transform them to be able to do a paired t-test. Maybe what I should instead be doing is a sign test. One more. So let's see. How's a Wilcoxon sign rank test? It's also very simple. You just say Wilcox test, put in the two different means we're interested in, and we acknowledge that they're paired. And so the Wilcoxon sign rank test with a correction tells us, again, consistently, like we've seen before, that we have a fairly strong confidence in arguing that those means are different. So what we've just seen is the difference between parametric and non-parametric tests. In general, it's nice to meet the assumptions of the t-test. We should try to do that. We should try transformations if it's possible. But they're not always going to happen. The reason to try is because the parametric tests typically have more power to detect differences that really exist than non-parametric tests. Parametric tests, in other words, may not be your first choice. Parametric tests are your first choice. Non-parametric tests are not going to be your first choice. And if transformations can't work, then we go ahead and go with the non-parametric tests. If there's clear differences that exist, you're likely to get a difference between those two different tests. If your differences are unclear, on the other hand, if you have vague distributions that are not obviously going to be normalized very well, the difference between a parametric and a non-parametric test might be really critical, and you might get very different answers. So I hope you see that t-tests are a way to go if your data are normal. If they're not normal, then we should be carefully trying to do some transformations, and if they're not able to be transformed, don't worry about it. You have some backups in both those cases, the Wilcox test and the sign test. Okay? So always first test the assumptions and then choose the appropriate test. And notice what we've done. We've walked through a number of these tests here, t-tests and their alternatives, in one fell swoop. And notice also that the R commands for those were not very complicated. They're fairly straightforward. Okay, we're going to move on to ANOVAs in the next lecture, but I hope that gives you some background on how t-tests work and why you would choose different ones under different kinds of questions, and how they might lead to some problems if we choose to ask the wrong t-test for the wrong question, and in fact what you can do to try to make data work better, and then also what you can use as a fallback in case those t-tests are not appropriate because your data cannot be normalized. All right, I hope that helps. We'll play around with this in the lab as well, and you can see how z-tests and t-tests work. That's it for now. Bye.